Okay, it looks like our numbers are pretty well plateaued for this evening. There'll be a few latecomers, I've no doubt. Um, well, I've had one or two comments of feedback about this webinar, and there's um, some people like it. Some people sort of ask questions about, where are we? So you have to have pen and paper, and you have to sort of follow as best you can, and then you have to try the questions afterwards yourself. Watching someone else do them in a very sort of, easygoing manner um, is great, and it encourages you to have a go yourself. But in the end, you've got to do it yourself. So note down the ideas. Don't note down all the sort of details and individual sort of letters and equations, but get the ideas so you can try them out. I know it's kind of you've seen it. It's quite hard sort of saying, right now I'll do it. But that's the way you sort of develop the skill. So make sure you jot down the ideas as Dr. French goes along, and then you can apply them yourself. Not necessarily tonight, but certainly over the weekend. Okay, so Dr. French, thank you very much.
Thank you very much, and good evening, everybody. So we're going to welcome to the British Physics Olympiad's BPhO Round 1 Training Enterprise Extravaganza. If you are new to this, welcome. If you've been to all the others, thank you for coming back. We're going to have a little look through, again, the 2023 Round 1 part 1. That's quite, I think, the nicest way in. We're going to start with the end of the paper today. So we're going to start with this question. So as Mr. Hughes have said, if you can get a piece of paper, ideally, if you can print out the little workbook, there should be a link in the chat to my little website where I've got one question per page as like a little workbook. If you could print that out, I think that's for the maximum enjoyment. However, if that's not something you have in front of you, a piece of paper will do. So what we're going to do, we're going to go through some problems really slowly and sort of really show in sort of like slower than real time how we might sort of answer one of these questions. And the idea is if you do that n times when it's a relatively large number, you can then speed up. But hopefully you can sort of see physics in action. And although obviously this is aimed at practicing and preparing for round 1, hopefully the spirit of all of this is how good physics is done, which is about building mathematical models of the world. All right, so what type of world are we talking about today? We're talking about two bowls which are going to be on the ends of a light thread, and they're going to be sort of floating in water. So I think before we do this, I'm just going to do the iceberg problem. Which for those interested in things like Titanic, etc., might want to do, which is what fraction of an iceberg is floating above and below the water. So I'm sure many of you have done this before, but if not, let's see how we might solve this. So here we go. Here's an iceberg, all right, floating above the water, and the bit I'm shading is the volume beneath the water. So what we'll do, we'll call that, I don't know, V1. And we'll call that V2. All right. And V1 plus V2 is the sort of total volume of the iceberg. So if we've got this in this situation, we might want to have things like the density of ice, because what are we doing? Well, we've got Archimedes' principle. That's the physics involved. So we have the weight of our iceberg, all right, which is going to be the mass of our iceberg times the strength of gravity. And on the scale of our iceberg floating in the sea, our strength of gravity isn't going to change. So 9.8 newtons per kilogram. Right. And then we've got an upthrust, which is the weight of fluid displaced. So that's going to be, let's just label this. So let's have rho water. Now I've looked this up, and seawater is 1029. Okay, it's slightly heavier, or slightly more dense than fresh water, kilograms per cubic meter. Whereas ice, because water is lovely and anomalous with all the hydrogen bonding, has a lower density. And rho ice, I'm just going to glance and look up. I did this in advance. 934. There we go. 234 will be very special ice. Okay, kilograms per cubic meter. All right, so we've got same water, but one's in a different phase. One's in the solid phase, and it's a bit lower in density. All right, so what we've got, so Archimedes says the upthrust. So this is the weight. All right, and this is the upthrust. Oops. Okay, and what we want is the weight of the fluid displaced. So that's going to be the density of the water times the volume. That's the mass of the water we displaced times the strength of gravity. So there we go. So we've got rho of water, okay, times the V2, which is the volume immersed. So that's the mass of the water times the strength of gravity. All right, that's our upthrust. So if this thing is floating, then our forces must be balanced. And Newton's second law, the mass times acceleration is the vector sum of force. So if in equilibrium, right, so what we've got, upthrust equals weight. So, and I guess from a sort of diagrammatic and a notation point of view, it's setting the densities of the ice and the water to be different symbols is the way to have lots of fun with not getting confused by this. So what are we going to do? We can say that rho water V2G is equal to the mass. Now, what's the mass going to be? Well, the mass is going to be the density of ice times the volume, so V1 plus V2. Okay, so there we go. So what have we got? We've got rho ice, we've got V1 plus V2, and G. Okay, so there's our Newton 2, upthrust equals weight. And what we can do is we can cancel the strength of gravity on here. And what do we want to do? Well, it might be a good idea to find out the percentage of the total volume which is submerged. So let's write down something like that, like, I don't know, percentage of iceberg submerged. Well, what's that going to be in terms of our data, our graph here? Well, that's going to be V2 over V1 plus V2. Okay, let's call that, I know, phi, something like that. All right, so it's good to sort of write down in words what it is we're trying to find. And hopefully with some legible writing, I'll do my best. Okay, so can we do that? Well, that's great. We already have that ratio in our expression above. So we can go hunting for it. So from above, so therefore what we've got V2 over V1 plus V2, all right, is going to be rho ice over rho W. There you go. And that's straight away. So if we work that out, what is it? So 934 over 1029, and that's now just a pure number. The units will cancel. I'm going to get my trusty calculator out. If you can see this, all our calculators in Winchester College where I teach are glued to a kind of, I hope it's a 60-30 triangular wedge, but maybe it's not a 3-5-4 triangle. We'll see. I have to measure it later, but we can't remove them. They're very hard to pocket. So 1029, what is that? And that is about 91%. That's about right. Yeah. So actually, my diagram is a little bit off. So only about sort of 9% of the iceberg is above the surface. So that's quite a startling thing to work out. There we go. So hopefully that's a nice little warm up. And now we're going to go and use this idea of upthrust to solve this problem. So there's usually quite a few of these kind of upthrusty problems lurking with the round one. If you find one, this is a 6 marker as well, so this will get you loads of marks. And they're often not too bad. So it's really just applying Newton's second law, usually in a sort of equilibrium situation. So all the forces add up in a vector sense, but we are involving upthrust. And I guess that's what makes it a bit different. So there's lots of text here, so we need to deconstruct this. So firstly, we're going to make a diagram. So let's go and draw one. So what we've got is we've got some sort of pulley first, a light frictionless pulley. So let's draw that. Here's our pulley. So you can have a go at this as well. All right, and we've got this sort of light inextensible string, the magic physics string. So we don't have to worry about the pulley and the string. Okay, so one end, all right, we've got some water here. Well, actually, it's a liquid, isn't it? I know it is water. Yeah, I think it's water. Pulley is lowered and ball floats on the water. There we are. All right, so here we are. Here's our water. That's water. All right, and that's air. All right, so we've got this other mass here. All right, so that's going to be mass B. And then we've got this sort of ballcock kind of thing, the sort of thing you find in a toilet cistern, which is partially underwater. So there we go. All right, and that's A. So let's label it. And what have we got? So we've got air, water. I'll put the sort of water in. We'll shade it like that. so we can see we're underwater, and that's a light inextensible string. So what that means is that we can ignore the mass of the string. So when we're talking about centers of mass, it's of the balls A and B. And if ball A goes up, B goes down by the same amount. So there's no sort of elasticity going on. It's not like a spring problem. And we've got our strength of gravity here as well, G. And I don't know if we're actually needing to use G, but let's say it's 9.8 newtons per kilogram. Right, so let's go and put some forces. So I think it's quite a good idea to use different colors for the forces. So let's have a look. So A, we've got this up thrust, UA, which is going to be the weight of fluid displaced. And then we've got the weight of this one, so WA like that. And then let's have the weight of the other one. Let's use a different color for that one. Let's go for green. So we've got the weight of B, and then we've got the up thrust of B. But we've also got the tension in that string as well. So let's have that's the tension pulling this one up. And there will also be the same tension in the string pulling this one up as well. Okay, there we are. So there we are. So those are our forces working on this one here. And so what we can do is, so we've got T as tension in the string. And we've got UA is the up thrust. So let's write down what those things are. So UA, that's going to be let's say the water is of density rho. All right, so that's going to be the density rho. We've got G, all right, times now what we call is F. So F is a fraction of volume A that is submerged below the water. All right, so VA and VB are oh, actually, that's who we are. So, oh yeah, the two balls of masses, volumes MAVA and MBVB respectively. I think that's supposed to be VB actually. I think that might be a little typo. I wonder if anyone else noticed that. There we go. Yeah, so VB is 50 cubic centimeters and VA is double that, 1,000. All right. And then it's got the masses as well. Okay, so let's just put all that stuff together, shall we? So rho G F VA. So F is the fraction submerged. So what we're doing is we're taking our time and we're turning all the things in the text into something that correlates to the diagram. And that is a really important tip. All right, and then you will, if you've been to this these seminars for the last few weeks, you've heard me say that many, many times. So UB, what's that? It's going to be the up thrust on mass B, which is going to be rho times G times the volume of B. All right, so that's, we'll just put that there in green. So volume VB. And then the red one, okay, that's going to be, that whole thing is volume VA. Okay, right, so what else we got? We got the weights. We've got the weights. So we've got WA, which is going to be MAG. Right, so it might not be a sphere. We're just told they're objects partially submerged. And WB is MBG. Okay, so I think those are all our inputs. Okay, there we are. All right, so we're now going to assume it's an equilibrium. And because we don't know the tension for one of them, we're going to need to use both Newton 2 equations for masses A and B, and then between them we can get rid of the tension. All right, and ignore the second part of the question, which says the thread's now replaced by a string. All right, so we're going to do the first bit. So I think we've got I sorted out. We've got our diagram. What fraction F of the volume A is submerged below the water? So we've got all our equations. So the only thing that kind of makes sense for us to use now, there's no sort of conservation law of mass or energy that makes sense. This is all static. So the law of physics we want to apply is Newton 2. So mass times acceleration is 0 because it's an equilibrium. So we're going to add up all the forces. So I guess when you're answering any physics question, I'm always asked what kind of law of physics is going to get you places. And for many situations, it's going to be conservation of mass or energy or momentum or charge. All right. And if it's not that kind of question, you're going to end up with looking at Newton 2. And there's not many other options, to be honest, until you get into sexy things like Lagrangians, but those are also conservations of energy, really. So there's not a number of, there's not many many mechanisms when you boil it down. So if we assume equilibrium, so oops, equilibrium. So let's do A first. So what we've got 0, and I think we'll go sort of upwards for this one. Upwards is positive, all right, because it's a vector sum. So what we've got T plus UA, all right, minus WA. Okay, so let's just substitute what those mean. So what we've got 0 is T plus UA, which is rho GFVA, rho GFVA, so the weight of fluid displaced, and then we're going to take away its weight, which is MAG. All right, so there's no kind of density of the objects here. We're just given the masses, and let's just write down what those are while we're here. So MA is 500 grams, so 0.5 kilograms. All right, MB, what's that? That is 390, so 0.390 kilograms. VA and VB, I think VA was 1,000 cubic centimeters. All right, so there we go. Oops, 1 liter. And VB, I think, was half that. There we go. Oops. Is that right? Oh, no, VB is 50 cubic centimeters. Right, so there we are. 50 cm cubed. There we are. I think that's all the bits. Right, brilliant. Right, so there we are. So that puts it all together. So that means that my tension, so T, is going to be MAG minus rho GFVA. Okay. Right, so we want to find F. That's the goal. So what's the goal? And sometimes it's when you've got these questions, you can kind of often get a bit lost going, what am I actually trying to find out? So F equals, that's our goal. So sometimes you might want to just write midway where we're trying to go, so you get lost in algebra. So let's look at B next. Okay, so again we've got 0. Let's just look at our diagram. Well, we've got T and UB minus WB, so it looks very similar to what we had before. All right, so let's put the numbers in. So we've got 0 is T plus, so UB is the weight of fluid displaced, so that's going to be rho GVB. All right, and WB is MB times G. So just before we can sort of find out what T is, then we can set this expression here. Let's call that number 1 equals number 2, which is our new expression. So what have we got? We've got T equals the mass minus the upthrust. Okay, hope that's all right. Hope you can all sort of see what's going on. Let's put some boxes around that. And then if we set 1 equals to 2, all right, so 1 equals 2. Therefore, we can cancel the T. All right, so what have we got? We've got MBG minus rho GVB equals MAG minus rho GFVA. And right, so we need to then sort of put that all together. So rho GFVA is going to be MAG minus MBG. Oops. And then what have we got? We've got, what do we want to do? We've got to find, oh, yes. Okay. So what have we got for F is, just double check on it. So, okay, that's all right. Yeah, I think that's okay. We just want to find V. We've got the other volumes. There's nothing I've got. I'm just looking at my notes here. No, I think that's fine. So we're going to take away. So what have we got? We've got for this one, and we need to add plus rho GVB. So if we then, what I'm going to do, I think what we'll do is we'll have another line here. I'll go sideways this way. All right. So we'll go up here. So you can sort of see where I'm going. So what have we got? So therefore, we've got our fraction F is going to be MA minus MB G, and we'll then divide that by rho GVA. And then we've got plus rho GVB divided by rho g VA. All right, let's just cancel a few things. So therefore our fraction, so G cancels there and there, that's all good. And our density cancels. So we could do this, doesn't matter what liquid we use. So it's going to be the difference in the masses, Ma minus Mb, over, the density does matter here. Okay, so that term it does. And then this one is just the ratio between Vb and Va. So there we go. So another thing to check is that whether we have things which are dimensionally consistent. And so we've got the ratio of the volumes. So that's just a unit. That's a dimensionless quantity. F is a fraction. And we've got a mass or mass difference over a density times a volume, which is a mass. Great. So that has no dimensions to it. So let's now put the numbers in. So what do we got? We've got 0.5 minus 0.390. We've got the density of water. I think it's water, isn't it? Which are told as 1 gram per cubic centimeter. Oh, I should use them in grams. There we go. Never mind. So let's turn it all in grams, shall we? So what do we got? We've got 500 grams minus 390 grams. There we go. Over 1.0 grams per cubic centimeter times VA, which is 1,000 cubic centimeters. So stick the numbers in, and we can see that we're going to get things to sort of cancel there. The centimeter cubes cancel, and then our volume ratio, that's going to be 1,000. Wrong way around. 50 divided by 1,000, and so I make that 0.16. Okay, so it's actually 4/25. All right. So there we go. So 16%, i.e. about 16%. Okay, so I hope that was fun. So basically, yet again, a Newton 2 kind of argument. We've got a kind of submerged system here. We've defined everything quite carefully. So we've got the upthrusts, but in this case, in terms of the fraction of volume of A. And there we go. So it's a bit like what we've just done with the ice ball. Right, so let's just finish it off. So we said, suppose a short section of the thread is replaced by a spring of negligible mass of spring constant. So all that we have to do now is to assume that the tension, so what we're trying to find, how much is the spring extended? Well, the tension is going to be our spring constant times x. So basically, that's all we have to do. We have to use one of those equations to find the tension, and then use tension is the spring constant times x. So in part 3, we've got T is kx, and K for our spring constant is 100 newtons per meter. All right. So what do we want to do is our tension, let's use from 1. So this one here. So we look back into the equations we've got so far. T is mag minus rho g f va. In fact, we could have used the other one, actually. It doesn't really matter. I might as well use that. Okay, so what do we got? And we want that in newtons as well. So we're going to have to use the right units this time. So MA is 0.5 kilograms. So 0.5 times 9.81 minus, so it's going to be 1,000 kilograms per cubic meter. I think I won't put the units in for these. Times 9.8 times 0.16. I think I use the exact fraction so we don't have any errors. So 4/25. And then we've got VA, which is 1,000 cubic centimeters. So there we go. So we'll need to have that. So what we've got is basically 1 kilogram. There we go. So that's going to be 1,000th of a cubic meter. And if we put all that in, I make that 3.33 newtons. So VA is 10 to the minus 3 cubic meters. All right. And therefore, our extension is going to be 3.33 newtons divided by our spring constant, which is 100 newtons per meter. So that's going to be 0.033 meters, or 3.33 centimeters. There we go. All right. So there we go. So a nice little problem. Lots of words, but that's how we kind of deconstruct it. That's probably a bit small to see everything, but that's hopefully relatively coherent. And you can see the kind of words and structure I put in there. So I think I've labeled my equations. I've written about assuming equilibrium. It's masses A and B. So we can kind of keep track of where we're going. And notice I not put any numbers in until right at the end, which is another big tip. Do we have any questions on the chat? And I hope I'm still broadcasting.
You are.
Anything in the chat, guys?
I think it's all been answered.
Fabulous. Right, so we're going to try something, and as Monty Python would say, John Cleese sat at a desk in some sort of incongruous environment, and now for something completely different.
Well, there is one question which might be worth asking about. Why is it not 2T in the string, as it's pulled from both sides? A nice sort of well-known question.
Right. Okay. So I suppose what you've got is that you want the forces on the individual objects. So that's why I've used some color here. I suppose it would be 2T on the pulley itself. So the pulley, if I draw, maybe I use black for that. So that'd be a tension here, and that'd be a tension here. So if you like, the reaction force on the pulley must be 2T. If we ignore a sort of well, there's no other forces on it, for example. But we'll want the forces individually on object A, the red ones, and then the forces on object B. So if the rope carries, or the string carries tension T, then you don't need to double it. So I think this is when you're looking at sort of connected objects, you can either take the whole system. In that case, the sort of tension would cancel, or you can take its subsets, and then you'll have a kind of connecting force. In this case, it's the tension of the string. So that's why it's probably a good idea to use different colors. So you're looking at the forces on different subsets of your whole object where you've got connected things. So I think we looked at a problem a few weeks ago. We had a kind of car and a trailer, or a tractor and a trailer, that kind of stuff. All right, so anything with strings or rods, this is how you do it. All right, we're going to do something totally different. I hope that's I can't see if that's an acceptable answer, but I hope that's all right. Right, so let's have a look. Let's have a look at this question. So we're going to do I. So this is a completely different kind of problem. Bear with me. You might as well close your eyes while I scroll up. There we go. There we go. Nearly. So, right. So we're going to look at a problem about lights and waves. Oh, hello. We're still going. That's all right. Yeah. Okay, good. Yeah, I'm still broadcasting, guys.
Yeah, all's good.
Yeah. Yes, I sort of had a bit of a glitch there. So we've got an 8-watt beam of light. Okay, so all right, as soon as I see thing, let's label it. All right, so let's call that power P. It's shown at surface at normal instance. So there we go, some sort of surface, and we've got some light coming to it. The surface reflects 50% of the incident light and absorbs the other 50%. All right, what is the average force exerted on the surface by the radiation? Now, this is interesting. So for those of you who've studied a little bit of quantum mechanics, photons are, so light is, you can think of as a wave, electromagnetic wave, a disturbance in the electric and magnetic fields which charges produce. All right, but we could also think about it as sort of packets of energy, which is a rather abstract idea. But this is the kind of guts, this is one of the key principles of quantum mechanics. All right, so very interesting branch of physics here. And we can think of these sort of energy packets, this sort of the electromagnetic ray having kind of discrete elements, and these being like particles which carry energy and indeed momentum. But crucially, they don't have any mass. So your idea of momentum being mass times velocity isn't true for photons, and yet it has momentum. So that's a bit of a mind-boggling idea. However, this is where we're going to start, right? So we're going to look at this like kind of particles colliding. But I guess the cool thing about this is we're talking about a laser beam or some sort of beam of light. All right, so we're told the average wave of the light is 600 nanometers. So let's label that. And we've got an area A that our light beam is incident on. Okay, so the volume density of photons in the beam. So how many photons per cubic meter? So how on earth would we go for this? Well, like at the beginning, I said, you've got your idea. What sort of conservation laws are going to be useful here? So can we conserve energy, charge, mass, momentum? Otherwise, it's a force question. Now, it asks us to look at force, but really, if you follow the hint, we want to think about conservation of momentum. All right. So for momentum things, we need a before and an after diagram. So this is what we're going to do. So let's draw our surface here. So if you're very new to quantum mechanics, this will introduce lots of interesting ideas. Okay, but we're going to start off with a paradigm. I've used that word before, a sort of mathematical model, which you can use for all sorts of things. So the mathematical model here is like bouncing balls, except these aren't balls, these are photons. So we've got a kind of photon here of momentum P, and that's my photon. And let's have a think. So we've got the energy of the photon E, right? So if we've got P joules per second, the number of photons is going to be P over E. Just think about that for the moment. All right. So if I just put that, that's the photons per second. All right. Okay. So we've got the energy per second, which is the power, divided by the energy per photon, which is given by E here. All right, so that will be what we call the flux of photons. Or photons. Okay, striking. All right, so we've got all these photons. They all have the same momentum. So P times big P. Now I need to be careful about my writing here, so I'm going to put little p there. That's all right. So we can almost imagine like a big ball of photons of that momentum. That's the total momentum. So that's before. So what happens after? Right, so after, let's just draw our thing again. Here's our surface. Right, so what we've got is we've got 50% of them. Now, what I'm going to do is I'm going to call 50% alpha a fraction. And I'm going to make this slightly more general than the question is. So if you're doing this at speed, you want to use the numbers. But I think we could be a bit more advanced by this. Given we're doing it slowly, let's say some fraction. So alpha is between 0 and 1 in our question. So alpha equals 0.5 here. All right. So we're going to generalize this. So what do we got? So how many photons per second? So this is essentially 1 second of photons, right? So, and if you want to look at like the force of anything continuous like air or water, what you do is you say, all right, what does 1 second of water or air, or in this case, photons look like? So consider 1 second of light of photons. That's what we're doing. All right. And then we're doing before and after. So 1 second of photons is like a basketball being thrown against a wall. that might be quite mind-blowing, but that's basically what we're doing. So what we got P times big P over E times alpha. But we've also got the wall here, and now we've got some recoil, should I say, not recall. So we've got momentum of the surface itself. So how many photons have been absorbed? Well, 1 minus alpha, big P over E times little p. And we've got some momentum as well. That's our impulse. All right, because now the thing about this question to make it tricky, and I'm pretty sure I made this error when I looked at this first time round. Actually, maybe that's I use a slightly different color than hot pink. There you go. All right. So it might be very easy to forget this because we notice that photons have been absorbed. So the idea, they still have momentum, all right? They don't lose their momentum. They're not just sort of staying there. It's not like an inelastic collision, like, you throw some jam against a wall, all right? Okay, the photons are still moving, all right? Just happen to be within the surface, right? But still carry momentum. Okay, and this is what makes this question a little bit sneaky. Right, so there we go. So this bit here I've highlighted that's the absorbed photons. So it's the momentum of absorbed photons. I hope that's nice and clear to see. All right. Okay, so before we carry on, let's just check that we understand what's going on. So do we have any questions in the chat about what we've done and how this might relate? Because obviously this is conservation of momentum, but we're using light here. So there's a few key ideas I've introduced. So any questions that need to be queried or answered?
Possibly another explanation of what flux is.
Oh, right. So something per second. I mean, sometimes it's something per second per unit area. But essentially what we've got here, big P over E, is the photons per second. So what we're looking at in this picture is 1 second of photons. And we want, so if the momentum of the photons is P, big P over E is the number of photons per second. And if we multiply those together, that's the amount of momentum per second that's colliding with the surface. So it's a bit like, you throw a basketball against the wall, and the basket, if you were, say, doing that to a gust of air, for example, 1 second of air, the mass of that, or rather say the momentum of that air, will be the same as the momentum of the basketball. Right? So we can use the same physics to describe both situations. So there's a recoil of the wall, just like we throw a basketball against it. All right, I hope that's all right. We use the term flux in lots of things, but essentially, define it as something per second. So sometimes something per unit area as well, but we'll use that a bit later. All right. Okay, so if we do conservation of momentum, let's change color for that one. Let's go for red. So by conservation of momentum, all right, what have we got? Well, we've got the momentum after E is equal to the momentum before. So what do we got? We've got 1 minus alpha. We've got little p, big P over E, plus the momentum change. And I'm going to use that as positive. All right. Then obviously the photons that have been reflected, that their momentum is negative in this sort of direction. So big P over E times alpha. And that's equal to the momentum that we started with in 1 second. Okay. So now we've got the momentum. So this relationship, the momentum of a photon. So E is PC, or P is E over C. All right. So that's a very interesting relationship there. Okay. It sort of relates to something called the de Broglie formula for particles. I think that might be just a nice little segue here. Actually, I think, do we use that a bit later? I'm just going to double check on my notes here. Yes, we use that later. So I think I'll talk about that in a moment. All right. So if we do that, all right. So if we got P equals EC, then we got this quantity here. What is that? So we've got P times big P over E. So let's put that together. So we've got E over C, there's a little p, times big P over E. So we can cancel the energy of the photon. And so that quantity is the power over the speed of light. All right, I hope that's all right. So now if we can put that all together, so this bit I've highlighted here, and this bit here, that's the power over the speed of light. I think that's all right. So therefore, what do we got? We've got 1 minus alpha. We've got big P over C. All right, plus the change in momentum, the recoil, the impulse. And then we've got big P over C alpha equals big P over C. And of course, we can cancel all of that. Or not quite, no, because we've got the momentum change we want. So therefore, my impulse to the wall is big P over C, that's the power. All right, and what have I got? I've got 1 plus alpha minus 1 plus alpha. I think that's all right. So the ones cancel, and that's going to be 2. Oh, hang on a minute. What have I done? Sorry, no, we've got 2 alpha there. The ones cancels yet. So 2 alpha times the power over the speed of light. There you go. So that is the momentum change of my surface. Okay, so there we go. Now, this is a sneaky problem because what it asks for is what's the force exerted on the surface by the radiation. So what we've got is we've got the impulse to the surface, but we've also got the absorbed photons as well. So to answer the actual question, we want the total momentum per second transferred. So the total momentum transferred per second, and because force is rate of change of momentum, that's what we want per second, all right, is going to be the recoil of the surface. That's the surface recoil plus the momentum that it had before, so that of the photons which have been absorbed, which is 1 minus, right? So minus alpha times P over C. Okay. So there we go. So this bit here, all right, this bit here is actually what we want. All right. So what we actually want, the momentum change is this lot. Okay. All right. So it's a little bit sneaky, this problem. Well done for the person who set this. So so what we've got, so 1 minus alpha, little p, big P over E is P over C. So if we just put all that together, so that's P over C, and that's going to be, so 2 alpha over, so 2 alpha plus 1 minus alpha, so 2 alpha plus 1 minus alpha times the power over C. All right, just carefully how I've done that. So delta P is 2 alpha big P over C. And then I'm going to add 1 minus alpha big P over C, which is this bit here. That's the absorbed momentum per second. And then if I put that all together, my alpha, so I've got alpha plus 1 times the power over the speed of light. Okay, now that's the momentum per second. So therefore, the average force, right, so the average force equals 1 plus alpha times the power over C. Now let's put the numbers in. So 1 plus 0.5, that's what our alpha is. What's P? It is 8 watts. So times 8 joules per second divided by the speed of light, which is very tiny. So let's call it 3 times 10 to the 8. And that gives you something very small. I make is 4 times 10 to the minus 8 newtons. So this is a little bit, it's by a more realistic model, I guess, of radiation pressure. So, you know, you can use the radiation from the sun, for example, to bounce off a solar sail and use that to propel you into the cosmos. All right. Okay. And then obviously the further you get away from the star, you know, the smaller that is. But in principle, if you have a big enough sail, you could reach very large speeds because, of course, there's no drag in space. All right. So there we go. But I suppose this problem is generalizing it because we are absorbing some of the photons as well. So you have to be a little bit careful. All right. Are there any other parts? So calculate the volume density of photons in the beam. Right. So how do we go about that? Before I carry on, though, are there any questions that have arisen from this little demonstration? Am I still there? Am I still broadcasting all right?
Yeah, we can hear you.
Right. So I guess this is rather nice because although we're talking about light, we're thinking we've used 1 second of light. So if you want to sort of, you're doing problems with like in fluid dynamics or aerodynamics, that sort of thing, we consider 1 second of air, like, you know, the forces on aircraft or racing cars or cycles or something like that. So what we're going to do for part 2 is we're going to consider 1 second of light, just like we did before. And how many photons we've got, it's a volume density. All right. So there we go. So let's assume we've got a beam here. This area is which is 12 square centimeters. All right. So in 1 second, how far does the light travel? Well, the speed of light. That's going to be C, which is 3 times 10 to the 8. So in 1 second, we've got an enormously long stick of light, which has been absorbed. So we've got N photons incident here. Now, what we've got, if we want to work out the energy density, we're going to use de Broglie's equation. So this is one of the key things in quantum mechanics. So this, if you're new to this, de Broglie, which is spelt de Broglie, but it's de Broglie, who I think was some aristocrat, I think. So E is Planck's constant times the speed of light divided by the wavelength. All right. So there we go. And I suppose if you can sort of like use E equals PC, all right, what you've got is therefore the momentum is h over lambda. And that is a very general result, which is not just true of light, it's also true for particles as well. So you may have heard about things like electrons have a characteristic wavelength. Well, if we can work out the momentum and we divide that with Planck's constant, we get the wavelength of that. And that's how electrons can diffract and all that kind of stuff. And Planck's constant is a very small number, which is why we don't tend to observe quantum effects on our scale. If you bowl a cricket ball at some stumps, it's very unlikely to pass through them without knocking the stumps over. So h is 6.63 times 10 to the minus 34. And if you look at the kind of units for this, we're going to have kilogram meters per second, all right, times meters. So that's going to be a squared there. All right. So that's our energy. So what do we got? We've got a number of photons. What's the number of photons? So we've got the power, all right? So the number of photons, the watts per second, times the, well, we've got the watts, we've got 1 second, so P, and then we're going to divide that by the energy, all right? All right, that's the number of photons per second. All right, so that's going to be, so we've got hc over lambda, and we've got a p here as well. Oh, wrong way around. That's a dividing sign. So we've got our power, and we're going to divide that by hc over lambda. And if we sort of reconcile that, that's the power times the wavelength, Planck's constant, times the speed of light. Now, what we want is the number of photons per cubic meter. Okay, and so what might that be? So if we say that n is n photons per cubic meter times the volume of our sort of stick here. Okay, so that's going to be our number density. So that's photons per cubic meter. So therefore, we can write those next to each other. So nCa is the power times the wavelength, Planck's constant times the speed of light. And then what do we want to do? We can work out n, which is going to be the power times the wavelength over c squared times HA. Yep, I think that's what I got last time. And so if we put all the numbers in, we can work out this number density, which is going to be a massive number, right? So it's 8 watts times 600 nanometers. All right, so that's the red end of the spectrum. 3 times 10 to the 8. We're going to square that times 6.63 times 10 to the minus 34. And then times the, where we want is 12, and it's square centimeters. So we need to have times 10 to the minus 2. All right. So I've converted centimeters into meters here. And that will give me, I put that in here, about 6.7 times 10 to the 13 photons per cubic meter. All right. So there we go, a pretty wild idea. So I think that's sort of the last one I'll do for a problem. I'm going to show you something a bit different, but there's loads of ideas in that question. So I think this is quite a hard one if you were going it straight away. In fact, even if you knew what you were doing, but there's lots of good stuff. So as a recap, what do? We had our surface. We treated this like a momentum collision problem, but we're talking about what happens in 1 second. So you can imagine a kind of stream of light is in 1 second. That's like a big particle, which is the momentum times the number of photons per second, and how that relates to power. All right, and then we've got this sort of sneaky bit, like conservation of momentum by the momentum absorbed, and then we've got the impulse, etc. All right, I suppose you could, all the thing that I've got on the left-hand side, if you like, you could have just said that momentum, but I think it's quite helpful to deconstruct this. And then we've done conservation of momentum. We've used our momentum of a photon, and we've put that all together, and we've worked out the average force, the momentum per second, the impulse per second, and then we've looked at sort of a slightly different way of thinking about it, like 1 second of light, how many photons would that be? A sort of big cylinder of light, if you like. Okay, so yeah, lots of ideas to mull over for that one. As I say, you can download that from my website, and I definitely recommend having another go at that if that's your first go. And this, De Broglie, is a lovely idea. And if you are very new to quantum mechanics, if you go onto the Eclecticon, onto the physics quantum page, there's all sorts of stuff. All right. Okay. So if there are any more questions, I'm going to show you something a bit new. Are there any questions that have come out of that, by the way?
I think they've all been answered.
Marvelous. Right. So I highly recommend a 3 blue 1 brown video called The Cosmic Ladder. Do I have this up on my screen at the moment? I think I do. There you go. I think it's this one. Oh, not quite. It's going to be one here. So is this going to load? Good. So here we go. So what I've done is I've made this little presentation. If you want to download this, if you go onto the Eclecticon, it is on here. All right. So this is the BPhO page. So here's my here's the home page of the Eclecticon. If you go to lectures and keep going, I think it's on the 4th page. There is this thing, the Cosmic Distance Ladder, which you can download and have a look at. What I've tried to do is sort of paraphrase this amazing 3 blue 1 brown lecture. So here we go. This is Terence Tao, who, well, I'm sure he'd be very humble, but I think everyone else in the world thinks he's the world's best mathematician. He's certainly very impressive on the video. And 3 blue 1 brown, that's the sort of link. There's rather a lot of subscribers. Anyway, so I think this is kind of what the ladder is. So there's basically 9 rungs, and the ladder is sort of how we work out the scale of the universe. And it's mostly in terms of distance, but of course, distance and time, the speed of light, you've got a temporal aspect as well. So the first rung is how the radius of the Earth was calculated. And a lot of this is sort of stuff that you could have done in ancient Greece if you had enough had decent clocks. And that's great because quite a lot of these rungs are things that you could do you know, with your own observations. You don't need a large hadron collider or a spacecraft to do it. So first one is calculating the radius of the Earth. The second one is the Earth-Moon distance. So I think what we might do in the next few sessions is we'll do a couple or one rung each time. All right. So firstly, the radius of the Earth. Now, some of you might know about this. This is a guy called Eratosthenes, who was around sort of 276 BC to 194 BC. He's got a particularly sort of a round head as well. So maybe, you know, that inspired him to calculate these things. And the idea was you looked at rays of light going to Alexandria. So Alexandria is over there, sort of in Egypt, modern day Egypt. And the idea is that Syene, which is not quite due south, the rays of the sun are directly overhead, and this well cast no shadow. So the sort of big idea is that if the Earth is a sphere, then the angle of the shadow, theta here, is also the angle between, so the arc between Alexandria and Syene. And you can sort of see that from this picture. This is from my book, Science by Simulation, #1. And you can see the rays of from the sun, which are part of parallel. And if you can kind of extend that line out from Alexandria, that's angle theta. And if you kind of have a look, then that also must be this angle at the bottom. So if you get, well, in those days they had slaves, which is obviously awful, but these days we call them graduate students. And that angle, you'd hire your cheap labor to work out the exact distance, r theta, if that's in radians. And then if you can work out the angle from here, you can work out what r is, in this case, the radius of the Earth. So that was about 5,000 stadia, which is about 5,000 times 185 meters. That's the distance between Alexandria and Syene. Really hard to measure because you've got bandits and crocs and you've got to cross the Nile. So that's a pretty epic adventure. But let's just say that was measured. And the angle's about 7.8 degrees. So I've converted it into radians here, multiplied by pi and divided by 180. And I get about 6.8 million meters, which would obviously be a fantastical sort of calculation for the Greeks because, you know, they wouldn't have obviously traveled the Earth. So, you know, there would have been probably many flat earthers in those days. So this would have been a very bold prediction, but only about 7% out, which is pretty cool. And you can do an even better method. This is about 1,000 years later by this chap called Al-Biruni. So the kind of, I guess, the intellectual movement sort of went from the Greeks and probably at the same time also in Asia as well. A bit later in South America, but sort of Northern Europe had a bit of a downturn in those days. And probably the Islamic world was probably really where it was happening at around 1,000 years ago. And so al-Biruni, he's from, I think, modern day Turkmenistan, Tajikistan, something like that. And so what he was able to do is use trigonometry. That's an amazing invention from India. And so he was able to sort of look at the same problem, but with a bit more detail. So the idea is you climb a mountain, and I've exaggerated this enormous mountain, sort of rumdoodle-like, although you can do it with Ben Nevis in the UK, if you're lucky enough to have a view, which rarely happens. But if you survey the height of the mountain, and this little thing in the corner is quite nice, because to work out the height of a mountain, you don't want to drill a hole in it. So that's very expensive. You measure a baseline, and then you measure at the end of that baseline the angle of elevation to the peak, which you can do with things called theodolites. This is how surveyors do it even now. And you use a bit of trigonometry, and using the tans, it's the product of the tans minus the difference, times that baseline. That gives you the height. So you can do this. And for Ben Nevis, it's 1,345 meters. And on the top of these mountains, they'll have a trig point, which until GPS was the way that we worked out heights and things. So what you do is you work out the angle of dip to the horizon, gamma, which is not very big. For Ben Nevis, it's 1.18 degrees. So for things like Mount Everest, it'd be rather larger. But let's just say al-Biruni would have had one of his servants to climb something a similar height to Ben Nevis. So you need to measure this accurately with like a big compass. And then you do some trigonometry. You say that r plus the height of your mountain, cosine that angle, is the radius of the Earth. So rearranging that, you get an expression for r involving the angle of dip and the height of your mountain. This is called al-Biruni's formula. And if you stick in the numbers for Ben Nevis, we get a much smaller error than we had before. So I think al-Biruni would have got the radius of the Earth within about 1%. And now then you'd have to take into some things like the fact the Earth is not very spherical. So that's what's one rung. And then so once we've got the radius of the Earth, 6,378 kilometers, how can we work out the radius of the moon and how far it is? And this is great, because the ancient Greeks knew that this is about 60 Earth radii. And in fact, if you have a basketball and a tennis ball, the ratio of the basketball to tennis ball is pretty much the same as the Earth to the moon. And if you have a modestly sized classroom, the distance between the basketball and from one end to the other is about 60 basketball radii. And so that's a pretty good scale model of the Earth and the moon. So when you go to your classroom, go find a basketball and a tennis ball, stick the tennis ball at one end of the classroom, basketball on the other end, and that's a good scale model of the Earth and the moon. All right. So how do we actually work out what that distance is? Why is it 60? So I've got a little diagram here of an eclipse. So eclipses tell you all sorts of stuff. And so we're going to be very careful about what times we're talking about here. So it's when the moon just about goes into the shadow of the Earth. This is a lunar eclipse. So that's called P1 on our little diagram at the bottom, which I obtained from Wikipedia. And then U4 is when the moon is just about to come out of the shadow. All right. So if we can work out what that is, so that distance that arc travels, the angle small, is pretty much 2 Earth radii. So if we can work out the time of that, so we can measure it, and it's about 208 minutes, something like that. So 208 over 60 hours. That's going to be the orbital fraction. So delta T over T. So if T is 27.3 times 24 hours, that's how long it takes the moon to go around the sun, right? That fraction there is going to be the arc length divided by 2 pi r, where little r is the radius between the Earth and the moon. So between the centers, right? So if you work out that fraction, 2r theta, so that's 2 times the radius of the Earth over 2 pi r, the 2's cancel. So you end up with the fraction of the time of the ellipse to the period is the radius of the Earth to pi times the Earth moon radius. So if you kind of put that fraction together, what you get is about 100 over 189. So our Earth, or should I rather way around? So r, the distance from the Earth to the moon, is 189 Earth radii over pi, which is about 60 Earth radii. So there we go. We'll do another one next time. That's a pretty cool thing. So literally, from timing your eclipse carefully and knowing the radius of the Earth, you can work out how far the moon is without having to actually go there with a spacecraft. So that's pretty awesome that we've known that for about 2,000 years. Obviously, they wouldn't have had great clocks in those days, but you could do that. So next time there's a lunar eclipse, Get your timers out. See if it's 208 minutes. All right. Thank you very much, everybody. Come next week and there'll be more. Well done. Do sign up for round 0 and I'll see you next time. Thank you. That's a lot of emojis. All right, you can go home now. All right, if we can stop the recording now, I think. Okay.
Okay,
Right,
good stuff.
participants.
Well done.
Yeah, if you can. Hi, guys. Time to go home. Get yourself a nice cup of tea.